Hello, everyone. Good morning, and welcome to a presentation about the state of GeoServer in the first quarter of 2021. In this presentation, we are going to talk about what's new in GeoServer 2.18 and what's coming in GeoServer 2.19. Focusing on GeoServer 2.18, we can see that we already performed a number of releases, in particular 2.18.0 in September 2020, and then 2.81 and 2.18.2 just released in January 2021. And we still have 3 planned releases going towards the end of the year when GeoServer 2.18 will stop being released around September. As you can see, GeoServer 2.18 comes in 2 main packages: the platform independent binary, which allows you to quickly try out a GeoServer by just starting a batch file, or the web archive, which allows you to install GeoServer in a web container like Tomcat. GeoServer 2.18 comes with a number of extensions that allows you to do extra things that are not part of core, like connecting to external databases such as Oracle, SQL Server, MongoDB, DB2, and so on, enabling extra cartographic options such as the CSS styling, enabling abilities to better control the load in production, such as control flow, and so on. In addition to these extensions that you can find in releases, there are also a number of community modules which are released only as part of the nightly builds and provide even more functionality for those that are interested in trying out the latest and the greatest of GeoServer. Coming to the improvements that landed in GeoServer 2.18.0, let's start with a few small but pretty useful GUI improvements. As you can see from the screenshots, we now have an apply button on most pages, which means you can click on the apply button and apply the changes that you have in your configuration page, say the current style or the current layer configuration, and then go verify if the changes work as you expected, as you wanted, without having to save and exit the page as it used to be. The cancel button is also pretty evident. It's clearly visually separated from the other two. And for pages that are very long, like the layers configuration page, we now have this ability to keep the save, apply, and cancel bar visible at all time at the bottom of the current visible area. Moving forward to GFL. GFL is our map algebra language. It has been shipped with GeoServer for a while now. In GeoServer 2.18.0, we have this new ability to generate multibound output. Previously, you could take as many rasters as you wanted as input and do algebra on them, but the output had to be single-banded. Right now, you can generate multiple bands in output instead. Let's have a look at a very simple script here. We have 2 input rasters, source 0 and source 1, that we identify as the before and after variables. So we are trying to make a time comparison. And we are going to generate an output raster which has 3 bands: the before band, the after band, and the difference between after and before. This map shows a possible usage of this script. We have a raster of the ship density in the Black Sea, so each pixel contains a count of the number of ships in that particular location. As you can see, there are routes in the sea. We have 2 maps at 2 times, T1 and T2, and we are generating a map of T1, T2, and the difference between T1 and T2. The map per se shows only the difference. It's red when it's going down and it's green when it's going up. But if you do a get feature info, you can get all 3 bands. The projection subsystem got significant improvements in GeoServer 2.18. In particular, we have the goods interrupted homologine projection support, which is pretty nice. It brings me back to my first years in school because all the geographic atlases were using this kind of projection to represent the world. What's interesting about the support for this projection is that it fully supports its interrupted nature by means of the advanced projection handling support. In particular, if we look at this map, which is a good interrupted homologene for the lens, and as you can see, it doesn't cut the lens all that much. It's just cutting over Greenland and over Antarctica. You can see that the polygons are properly cut at the interruptions, that they are densified in order to generate curved outputs. What's even more interesting is that the blue area is not a background value. It's actually a very large multi-polygon, a very large C multi-polygon. So that complex polygon has also been cut and densified to generate the lobes of the interrupted homologene. Another improvement that we made in the projection subsystem has been to improve the advanced projection handling for the azimuthal equidistant. This is important to support the Equi7 grid system, which is a set of 7 azimuthal equidistant projections covering specific area of the world with low distortion. This is pretty useful to take raster data, reproject it in a equidistant projection, and then do raster analysis on top of it without caring too much about the projected nature of the data. Originally, the projection was supported. It already had advanced projection handling, but the polar case was not properly handled. And we can see that in GeoServer 2.17, we are reprojecting nicely. Here we have the entire world. We have a data set that covers all the countries coming from natural Earth. And the little hole that you see in Antarctica is due to the fact that the original data is expressed in 3857 Web Mercator, and thus it cannot touch the poles. Another interesting new functionality is the features template module. It used to be called JSON LD, but in GeoServer 2.18, it has been improved and extended so that it can generate GeoJSON 2, and it has been thus renamed to features template. What does it do? Well, it takes as input simple features or complex features, it doesn't matter, and uses a JSON template that you can edit to generate either a JSON LD or a GeoJSON output of your liking. So you can take whatever input structure you have and remap it just for JSON to the desired output structure. This is becoming more and more important and more common. In these days, we are looking at supporting OpenSearch4io GeoJSON and stack items, which are two JSON ways to GeoJSON ways to represent satellite data information. Each JSON language represents the area of a satellite image, the sensor description, information such as snow cover, cloud cover, off-nadir, Doppler frequencies if we're talking about a SAR image, and so on. So each of these JSON structures provides more or less the same information, but in a different structure, having different attribute names, having different object nesting, and so on. So we are likely going to use the JSON templates to support these two new, let's say, output languages on top of the existing OpenSearch4io module, which is a community module, and which currently supports only GeoRSS output. During the months of developments of GeoServer 2.18, we worked a lot on GeoPackage improvements. In particular, GeoSolutions has been participating to the OGC testbed 16 and has been working on the GS GeoPackage community module, which contains a WPS process that can produce GeoPackages, to add a number of extra new features, such as embedding metadata and styles, increasing the writing speed, adding support for enumerated attributes, support for generalized tables, and for geohash sorting. Let's have a look at each of them in turn. So if you are familiar with GeoServer and you have configured layers a few times, you might have noticed that you can link to metadata from the layer configuration. And these links are going to be displayed in capabilities documents, which means the client can use them to figure out more information about the layer and the dataset. When we are extracting a GeoPackage, it's interesting to take the metadata and embed it into the GeoPackage, because the use case for the GeoPackage might be an offline use case. That is, you download the GeoPackage with your mobile appliance, and then maybe you go in an area where you don't have any reception and you want to have all the information you need to work with the GeoPackage inside the GeoPackage without having to connect to any external data source. So the first improvement was to take the metadatas and download them and stick them into the GeoPackage metadata table, which is a standard table in the GeoPackage format. Similar to metadata, it's interesting to have the styles to properly display the information. So here we have an example. The dataset is OSMasterMap topography, a very large dataset that is commercially distributed by Ordnance Survey, covering the entire United Kingdom at a very high level of detail. The dataset comes with 6 layers, and there are 4 different ways to present them. Let's say as layer groups of sorts. So you got the 6 layers, the proper stacking order, and the styles, SLD styles that you can download from the Ordnance Survey GitHub repository, coordinated with each other, generating 4 different types of maps: the backdrop, light, outdoor, and standard renderings. Now, if you are going for an offline use case for your GeoPackage, it's interesting to have the styles inside the GeoPackage. This has been done in testbed 16 using a number of extensions, some of which are not official, but have been in development for a few years during the testbeds. So one is the portrayal extension, which allows to store in the GeoPackage the style bodies, eventually with multiple languages, but also the style icons, so that the rendering can work in a fully self-contained environment. The styles can then be associated to the tables, to the layers, using semantic annotations. Semantic annotations are a way to tag either tables or rows in tables to give them extra meaning. The thing is, if you use the same tag to tag multiple entries in your database, you are basically creating an association. And we have been using semantic annotations to create many-to-many associations between the tables and the styles. In addition to that, we stored, as part of the metadata table, operational pictures, that is, the stack of layers and the right styles to use along with the layers. And this is stored as an OWS context in JSON encoding as part of the metadata tables. With all these 3 information sets, a client can open the GeoPackage, go to the operational pictures, figure out which layers and styles to use and in which order, go to the portrayal tables, actually get the styles and the icons, and perform a complete display of the map with the various styles. Now, coming back to OSMasterMap topography, it's a very, very large dataset. As I said, it's just 6 tables, but it stores something like 500 million records. When we turn this dataset into a PostgreSQL database, the database used 300 gigabytes of disk storage, which is roughly the size of a worldwide OSM database when we use Imposan to create such database. So imagine the amount of detail that we have to cover just the UK with that size. Now, writing out OSMasterMap as a GeoPackage before testbed 16 was taking well over a day. I actually don't know how much, because I never let it finish. After 24 hours, I just typically stopped it and worked on some optimizations. Now, after testbed 16, we can write the same GeoPackage in around 9 hours, which is a significant improvement. In addition to that, the OSMasterMap dataset has a lot of attributes which are actually enumerated. They got like 10, 15, 100 different possible values, but that's it. So there's an opportunity to compress the data, the data representation on disk, by just using integer numbers and have a lookup that tells you what's the meaning of each number. Well, it turns out GeoPackage already has that as part of the schema extension, which is one of the extensions which are included in the GeoPackage standard. The schema extension can describe the attributes of a table and provide an enumeration for each. Leveraging it, we found out that while PostgreSQL stored the database as 300 gigabytes and GeoPackage without enumerations used like 250 gigabytes, with the enumeration, we went down to around 205 gigabytes, which is a significant improvement. If you're wondering about the size difference between PostgreSQL and GeoPackage, it's because SQLite itself has a more compact storage representation on disk, mostly because it has been targeting mobile and embedded usage for so long, so environments where space comes at a premium. So it has a more compact representation. Here is an example of what's going on when using enumerations. We got the boundary line table and accuracy of position attribute. We can see values of 0 and 1. If we go to the standard GeoPackage data columns table, which provides information about the data columns in a table, we can see that there is a constraint, which is an enumeration, and we can go into the GeoPackage data column constraints table and find that it's an enumeration with values 0, 1, 2, 3, and more. And for each one, there is a description. So that's how we provide full information about the enumeration in the GeoPackage. Another interesting thing about OSMasterMap is that several of the attributes are multi-valued, which is typically represented in databases either as a secondary table or in more modern databases such as PostgreSQL as an array column. Now, SQLite doesn't have an array column. However, there's a commonly supported extension which is built into SQLite, which is called JSON1, which allows to use JSON documents in queries. So select elements of the JSON and perform queries on top of it. So what we did was to store the arrays as JSON arrays. And if the array content was enumerated, we used the enumeration support to further reduce the size. As a result, we have a full representation which is queryable. However, it's a testbed 16 specific approach. It's not part of the GeoPackage standard yet. It has been provided as feedback to the GeoPackage SVG, and hopefully they'll add support for it in a future version. Another thing that we have been working on since the dataset was so large has been Geohash sorting, which is a technique that we basically stole from PostGIS and in particular OSM usage in combination with PostGIS. Here's the thing, when you have such a large data set, moving the data and extracting the data from the disk becomes a significant chore. The file system caches of the operating system are not large enough to hold the data set. So if your data set is partially indexed, which it normally is, you have a way to quickly locate the parts of the data that you want, but you still have to load them from disk. If data sets which are close by on the map are spread around on the disk, you have to pay the price of many reads. if your disk is a spinning one, the price is very high due to the latency time of moving the disk head. But even if it's an SSD, you are still loading more information that you need because disks store information in blocks. If all the information is close by, you end up reading very few blocks. If the information is spread around over several blocks, you have to read them all. And in fact, we did benchmarks, and the Geohash sorting provided improvements also on SSDs. So what does Geohash sorting do? Well, basically, for each polygon line and point, we computed a geohash for that geometry, and then sort the records based on that geohash, which is a string. This has the side effect of moving information which is partially closed, also closed on the disk. Also, it's pretty interesting because it does not require a new GeoPackage extension. It just happens to be a better physical layout of the tables. So every client benefits from it. The benefits are, in particular, very important, very, very significant if the data set is very large, like much larger than the memory available to the operating system. And it's not so visible if the data set can be instead partially loaded in memory or fully loaded in memory. Moving on, we also played with generalized tables, which is yet another common approach in OSM rendering. So for this one, we played with the Ordnance Survey Zoom Stack, which is a free 10 gigabytes GeoPackage download containing a variety of layers which are meant to be displayed at various scales in different ways. So as you can see from these maps, we have significant scale dependencies. Now, the thing is, when you are displaying roads at when zoomed out, you only want the highways, the motorways. And when you start zooming in, you start including regional roads and then local roads and then all kinds of roads and paths when you are very close to the ground. So a typical approach that is used when rendering OSM, if you have been playing with Imposum, you probably are familiar with it, is to create generalized tables. Now, generalized tables are a simplified version of the main table, which contains first simplified geometries, which is useful, but much more important is that these generalized tables contain less records. They contain only the records that are meant to be displayed when you are at a given scale range. This GeoPackage extension basically provides the generalized tables and a lookup table, the GeoPackage the generalized table, which contains a lookup between the primary table, the generalized tables, and the range of scales in which the generalized tables are meant to be used. Using this approach and using a mobile client for testing, we found speedups up to 100 times in rendering speed, depending on the dataset. Some datasets are very significantly affected by this, like this waterlines table, which goes down in a very significant way in terms of record count when using the generalized tables, and affected less and less if the generalized tables contain more and more records. So it really depends on the dataset and the styles that you want to use for display, but it can be pretty useful. If you're interested in this GeoPackage work, we have for you a 10 minutes video presentation loaded on the OGC GitHub, describing in detail the work that we did for the GeoPackage server in testbed 16. And you can get even more detail by reading the testbed 16 GeoPackage engineering report, which is also linked from this page. And the slides will be made available along with this video. Now, let's switch to GeoServer 2.19. What's going on with 2.19, which is going to be released next month in March 2021. So in summary, there is a lot of movement when it comes to modules. We have a number of modules that are graduating from community to extensions. We have some modules going down from extension to community. We have new modules in the community land, and we have some modules which are going to be removed permanently from the code base. Let's have a look at each one of them. So the first one, graduating from a community status to official extension, which is going to bring it into the release, is the GWC S3 module. The GWC S3 module is a blob store that is this ability of GWC to store tiles. So a blob store is a plugin that allows GWC to store tiles in some storage. The default one uses the file system, but we have plugins for S3 like this one, and we also have a plugin for Azure and another one for Swift, and more could be built to accommodate other cloud environments. So this module, the GWC S3, is obviously interesting when you are deploying GeoServer in Amazon, and you wanted to store the tiles in S3 to save on the cost of storage. So you can have your cluster of GeoServer providing tiles through WMTS or OGC API tiles, and then store all of the tiles in S3. Another module that is graduating is WPS download. The WPS download module is a set of WPS processes that are built to replace WFS, WCS, and WMS for large download workloads. Why is that important? Well, WFS and WCS allow for download of raw data, both in vector and raster form, but there's a catch. The requests are synchronous. If you're trying to download something like a GeoPackage or a shapefile or anything that has to be fully prepared before the download, your client is sitting on an idle HTTP connection for maybe minutes, and these connections have a tendency to time out. If you need to do this operation, it's much better to do it on an asynchronous request. And here comes WPS to the rescue, because WPS is the one protocol in the OGC services that supports asynchronous request. So the GS download process can be called from a client, say MapStore, our own JavaScript framework for doing clients. And it makes the request, it gets back a status link that it can pull every now and then to get the status of the download progress. And when the result is finally ready, it can download the result without any HTTP timeout ruining your extraction. Now, along with the download of raw vector data and raw raster data, we have the download map and the download animation processes. The download map allows for large map downloads. Say you are displaying a map on a very large screen or a multi-screen setup, and the map is probably tiled, and then at some point you want to download that map for offline display usage, and you want to download it fully. So what do? Well, in that case, you can use the download map process to generate a single image, a single very large image. Eventually, with external layers, if there are external layers, GeoServer will WMS cascade them also in the request. So you can rebuild the same layer stacking that you have on the client to generate a final image for download. The download animation process adds on top of the download map abilities a link to a time series. So you can provide a set of times, a list of times, and the download animation process will generate an animation, an MP4 for you, scanning through all the times and generating this animation, which you can then download. Of course, it might take quite some time, so it's useful to do it on asynchronous request. Staying in WPS land, we have the WPS JDBC module, which is a WPS status storage. We just talked about asynchronous request. Now, say we have a map store making one download request against a cluster of GeoServer that are sitting behind the load balancer. So one of these nodes receives the request and starts processing it. And then MapStore starts polling, asking for the status of the request. If the request comes to a node in the cluster that's not executing the request, it might not know what to do about it. We need a way to share the status. The WPS JDBC module is a way to share the status of active requests in a relational database. Moving on, another module which is graduating is the params extractor module, which is a tool to literally smuggle vendor parameters into capabilities URL and force an aware shrink-wrapped GIS software to use them. So let's make an example. Say that we want to provide to a customer or a colleague using QGIS or ArcGIS a map, but we want to add a SQL filter on top of it. So what we can do is to use this parameter extractor approach to give them a link, eventually a capabilities document link that has in the path the parameter that we want to extract, like this H11, and then extract the params extractor module to take this parameter, which is on position 4, and turn it into a SQL filter, applying a transformation. Now, this is gonna turn the parameter into a SQL filter without the client realizing it. And this basically allows general usage of vendor parameters in shrink wrap applications such as QGIS. When you use them in this way, you can give the client a capabilities document that contains the H11. GeoServer will reflect that H11 into the backlinks of getMap, getFeatureInfo, and so on. And the client will literally use it in every request without even realizing. Another module, the final module, which is graduating, is the WPS multitheme module. It's an extension that we have been working along with OGC in testbed 12, and that improves the WPS protocol to add extra requests on top of the WPS existing ones. In particular, this new request allow to explore dimensions such as time, elevation, and custom dimensions. Try to picture a use case in which you have several dimensions, so a 4 or 5 dimensional data set, a data cube. And you are trying to figure out which are the possible times, and maybe the possible times are scattered and they are, let's say, many, like 10,000 or 100,000. And maybe they are correlated with space, such as satellite imagery. You have many times of collection of the satellite imagery, but if you are focusing only on a certain area, the set of valid times is a subset of all the valid times. So typically, when you have these data sets, dimensions are large and they are correlated with each other. So we have these extra requests that can be used to drill down into the dimensions and figure out the structure and correlation. The describe domains request in particular allows to list the dimensions and provide a description for each. The get domains values provides a list of values of a particular dimension, eventually filtering on ranges of values for the other dimensions. So you can ask questions like, what are the times available for this bounding box? Or what are the times available for this runtime? Say you are running weather forecast. The weather forecast have a target time and a runtime, and they are correlated with each other. So for a given runtime, you typically have only a set of predictions, so a set of target times. So fixing a runtime generates a very small subset of possible times, and vice versa. If you fix the time, you get a very small subset of possible runtimes. In addition to that, you can also run histograms. So you can ask the system to produce a count of how many possible times you have for each time bucket. Let's say you are displaying a time bar with weeks or months, and you wanted to display how many single data items you have in each one of them. Well, the get histogram request produces exactly that. This is used by both MapStore and the GeoNode to work with the time-enabled dataset and allow for animation control, timeline view with histogram, and all of this works with a filtering, a dynamic filtering based on the current displayed area. So if you zoom in, the time bar and the histograms will adapt to show you in which possible times you actually have data in that area. Now, moving to community modules, we have one module going down and being removed, which is S3 GeoTIFF, and another module taking its place, which is called COG. COG stands for Cloud Optimized GeoTIFFs, and they are typically GeoTIFFs with a precisely laid out structure, which helps downloading only parts of the GeoTIFF using HTTP range requests. This can optimize in a very significant way the data transfer between a HTTP storage such as S3, and your server. The COG module does exactly that. Uses HTTP range requests to download only the parts that are needed out of COG for display in GeoServer, leveraging the particular COG structure to minimize the amount of data transfer. In particular, the COG module adds support for the GeoTIFF reader and for the image mosaic so that they can point to COGs stored in a HTTP server or on S3. And it also adds support for the REST operations, in particular the harvesting operations, so that you can point your GeoServer to a new COG, which is just landed on S3, and have it harvested in your image mosaic with all the georeferencing and time and whatever other attributes you want to add into it. This is a significant improvement on top of the S3 GeoTIFF module, which was the first attempt to support COGs in GeoServer. It actually didn't leverage the structure of COGs at all. It was just downloading chunks of regular chunks of the GeoTIFFs as it needed them and caching them on disk. So if the default was to download chunks of 5 megabytes. So if you really needed a few kilobytes for the, let's say, the last overview, the smallest overview, you would still end up downloading 5 megabytes or even 10 megabytes if it was across 2 chunks to display the data. Another pretty interesting functionality that has just landed in GeoServer 2.19 is support for DGGSs, discrete global grid systems. Discrete global grid systems are hierarchical, sort of equal area tessellation of the world, typically based on rectangular zones or hexagonal zones or maybe triangular zones. The tessellation covers the entire planet with no special places or special lines like the dateline or the poles, so it has no difficulties handling the, let's say, the roundness of our planet. And it's typically hierarchical, so each zone has children's zone and grandchildren's zone, providing a multi-resolution view of the dataset that you decided to represent using the DGGS. The first thing that we did in testbed 16 again for DGGS was to take 2 DGGSs, RealPix and H3 by Uber, and generated this store that just provides the geometric representation of the zones. It doesn't have data. It just tells you, oh, okay, at this resolution level, here are the zones, the possible zones, and here is the zone identifier and eventual attributes like in H3, for example, whether it's a pentagon or a hexagon, and in RealPix, there is a standard way to color them, so it contains the color and type of cell, whether it's a square or a triangle and so on. And using this store, we prepare visualization that help understanding the structure, the geometric structure of the DGGS, such as parent-child relationships and neighborhood relationships, and figure out also whether there is some regular structure in the cell identifiers, which is pretty visible in RealPix and not so much in H3. Once we had a better understanding of DGGSs, we created a data store that can actually store data in DGGS format, which means that you have a cell identifier or zone identifier providing the location of the data and then a set of attributes attached to it. For this approach, we use the ClickHouse, which is an OLAP database. OLAP databases are geared towards analysis, and this is pretty interesting because DGGSs can provide on-demand analysis at the desired resolution level. We're going to talk about it. It's pretty cool. The other pretty interesting thing about ClickHouse is that it doesn't have a classic spatial database support, so it doesn't have spatial indexes, but it has a pretty interesting ability to partition tables and then run queries in parallel over the partitions. And the partitions can be running on a single node or on multiple nodes. So that means that when you are running a large query or a large aggregation query, if you are running analysis, it's literally spread out over all the possible cores available in the server. And if you are on a multi-node setup, spread out over the grid, speeding up the calculations dramatically. So on top of this store, we built a DGGS OGC API, which allows for download of the zones and their data. And this one is interesting because it's somehow reminiscent of the OGC API features, but add extra resources to navigate the DGGS structure. For example, we have a resource allowing to get all the neighbors of a given cell, or the children and grandchildren of a cell at a target resolution. Another thing that it can do is to take a real-world polygon in geographic coordinates. This is the Australian Capital Territory area, the area that contains Canberra in Australia, and map it using a minimum amount of DGGS zones. Here we have an example for RealPix and an example for H3. So this is kind of a way to get a minimal representation of the area using zones at a given target resolution. Now, DGGSs are pretty interesting for analysis because when you start using a DGGS and you have this multi-resolution notion, you can prepare a multi-resolution database of your data and then perform the aggregations and the analysis at the desired zoom level. Picture a use case where you have your Jupyter notebook talking to a DGGS API that can run analysis. So you start preparing your Jupyter notebook and prepare all the calls. And since you are sort of in development mode, you want to iterate quickly. So you run your Jupyter notebook asking for a low accuracy, which also implies fast execution because the number of cells involved in the analysis is small. And when you are happy with the results, you can grow your resolution and get more and more accurate results, aggregating more and more cells. So to run analysis on top of the DGGS, we adopted the Data Access and Processing API, which was another API being developed in testbed 16. This API allows aggregation, multiple types of aggregation on a given layers based on a space-time filter. So you can say, okay, given this area, compute the average value of an indicator for the past 50 years. So this is a time aggregation focusing on an area. Or you can do the opposite. Give me the average temperature in these points over the last 50 years. So you allow the entire area and you aggregate over time, generating a new point layer that contains the averages over time. Or you can do both. You can aggregate both on space and time and get a single value, a single average. So that's what the data access and processing API allows for. We built an implementation of it based on DGGS, which allows to run all these aggregations on the desired resolution. So on top of the DAP API, which others have implemented either on raster data or on vector data, well, we implemented it on top of DGGS's, allowing to choose the target resolution so that you can run a quick analysis over a low resolution, which is blazing fast, or take a bit more time and run it on a large set of cells at a high resolution. Actually, it turns out that thanks to ClickHouse, the aggregation can be really, really fast. So for example, we ran a space-time aggregation over 16 attributes, which were the 13 bands of a Sentinel-2 dataset, which we mapped onto DGGS structures. It contained 9 million records, and the ClickHouse aggregated them on a single machine in less than a second. And the single machine has a set of write disks, but they were spinning disks. Of course, the server had multiple cores, and ClickHouse used them all to run the aggregation. If you are interested in learning more about this topic, we have a dedicated 10 minutes presentation on YouTube, on the OGC Testbed 16 YouTube. And we also have 2 engineering reported, the DGGS1 and the Data Access and Processing 1, available as results of the Testbed 16. Closing up, what about the modules that got demoted and removed? Well, the script module was a module that allowed to write scripts for GeoServer plugins, such as WPS plugins and other types of plugins in Python, JavaScript, and Groovy. It was pretty interesting. Unfortunately, it fell unmaintained for several years while GeoServer kept on moving on, and eventually could not compile anymore, and we had to drop it. We have been waiting for a while, hoping that someone would step up as the new maintainer, but no one came around, so we had to drop it. The ArcSD's Datastore is also going the way of the Dodo, because, well, on one side, ArcSD is no longer supported by Esri, and on the other side, the module providing the Datastore access was also left unmaintained for several years. A module which is downgrading from extension to community status is the ImageMosaic JDBC1, which can read rasters from databases such as PostGIS raster or Oracle raster. This module is going down because it's no longer maintained. So one of the requirements for keeping a module in extension is to have an active maintainer, and this module hasn't had one for a few years now. So we had no other choice but to drop it to community status. We hope that someone will come around and become the new maintainer of the module. If that happens, it's gonna go back up in extension status. If it doesn't happen, well, eventually it will have the same fate as script and ArcSD, and it's gonna be removed. And that's all. If you want to contact us, please use whatever channel is more suitable to you. We have the contacts page on the GeoSolutions website with several options, or even drop us a message on Twitter. Thank you for listening and have a nice day. Bye-bye.